In this video, we're going to look at solving logarithmic equations that lend themselves to the uniqueness property. Now, if you have forgotten what the uniqueness property is, it says when you have single logarithms, so an equation where you have single logarithms on each side, and you've got the same base, then the arguments are equal to each other. Now, this might not seem powerful when you just look at the property itself, but we're actually going to use that to solve a problem like what we have here. So we have two problems that we're going to solve. Alright, so the first thing is we can't use the uniqueness property yet because we don't have single logarithms on each side. I have a single logarithm over here, but I need to have one logarithm there, and then that's where the logarithm properties or the rules come in. In this case, the multiplication rule, or the product rule, sorry, my bad. And what the product rule says, if you're adding two logarithms that have the same base, you can write that into a single logarithm, and what goes in the argument is the first argument times the second argument. So that's what I'm going to do. On this side, I will now have a single logarithm. So I still have that on the other side. And I'll have a product, and the first part of my product is going to be 4x minus 2, then times x minus 2. Now I can use the uniqueness property because I now have single logarithms on each side. So by uniqueness, the arguments are equal to each other. So now to solve this, I am just going to FOIL this through. So that's going to be 4x squared minus 8x, then minus 2x, and plus 4 is equal to 4. So my 4's cancel. And I'm going to have 4x squared, and then negative 8x minus 2x is minus 10x. Okay, so again, I could try and solve this using quadratic formula because my constant term would be 0, but it's not too hard to factor. The 4 and the 10 have a 2 in common, and then x squared and x have an x in common. So if I factor out a 2x from each term, what I'll be left with here is 2x. And if I factor out a 2x from that, or divide that by 2x, I'm going to have minus 5. Okay, and so now what will make this true? What will make this expression equal to 0? Well, if x itself is equal to 0, I have 2 times 0 times something else. Doesn't matter, the whole thing goes to 0. Or in here, if x is 5 halves. Because 2 times 5 halves, well, the 2's will cancel, and then I'll be left with 5 minus 5. So those are my zeros. Now the question is, are they allowed in my solution as solutions to the original equation? And in the original equation, the arguments must be positive. So 4x minus 2 has to be positive, and x minus 2 has to be positive. So now, if x is equal to 0, this becomes 4 times 0 minus 2, which is negative 2, which is not positive. So 0 is an extraneous solution, and it's not a solution of the original equation. We must reject it. Now what about 5 halves? well, I'll have 4 times 5 halves minus 2. And 4 divided by 2 is 2. Then I'll have 2 times 5. So that is equal to 10. And that equals 8. And that is a positive number. So far, so good. But all arguments have to be positive. And then 5 halves, if x is 5 halves minus 2, which is 5 halves minus 4 halves, is going to give me positive 1/2. And that is, now it's satisfied both of those, so it will satisfy the original equation. And so my solution to the original equation is x equals 5 halves, or you could just have it written as a solution set. Okay, so let's go on to the next problem. All right, what about this? Again, all terms are logarithms, so if I could have a single logarithm over here, then I could use uniqueness to solve that. So I want to write that as one logarithm, and I can do that using the quotient rule, which says if you have a difference of 2 logarithms that have the same base, then you'll get a single logarithm and it'll be a quotient, and this will be your numerator and that will be your denominator. That's the quotient rule. So I'm going to apply it over here. So I will get a quotient, that's my numerator, that's my denominator. Now I have single logarithms on each side, so I can use the uniqueness property. And uniqueness property says if you have single logarithms on each side, they have the same base, then the arguments are equal to each other. Now I need to solve this for x. I have an expression here where x is in the numerator and denominator, so how am I going to proceed? I proceed by getting rid of the denominator. And the way I do that is I multiply both sides by whatever the denominator is. Understand you cannot cancel x in that fraction. Cannot do it. You have to have a product in the numerator to have canceled that, and we don't. So, by design, those cancel, and I'm left with x plus 1 equals 29x. Now, I might flip that because I want that over here. Okay. Now, if I'm solving for x, I just swap sides of this equation, which is fine. I'm going to get everything with x on one side. 29 minus x is 28x. And now to solve for x, I divide both sides by 28. Now, is this answer allowed? You have to check it in the original equation. Is it in the domain of the original equation? Well, the arguments must be positive. So x plus 1 has to be positive, and x has to be positive in this case. Now, 1/28 is a positive number, so that's satisfied. And the fraction 1/28 plus 1 will also be a positive number. So that checks everything that we need. See, there's not an x over here, so I don't have anything more to check. Yes, it is allowed, and so this is our answer. That is the solution to that problem. Okay, so that concludes this video of solving logarithmic equations using uniqueness property. You can use uniqueness property when every term is a logarithmic term.